Okay, welcome back to the wild world of sediments and sedimentary rocks. This is part two. You should have already gone through part one. In part two, we're going to talk about the development of sediment and the weathering process, both physical weathering and chemical weathering. As far as the pictures go, uh, one picture shows me standing in the capital city of Buenos Aires in the country of Argentina. The pictures at the top, I'm looking at sediment composition at Ushuaia. Ushuaia is the southernmost point in the country of Argentina. Beyond that is the ocean, and the next stop would be Antarctica. In terms of the rock cycle, which we discussed in part one, we're going to concentrate on the process of weathering as it is circled on the diagram. The picture on the left is an example of physical weathering. You can see sediment being transported down this ravine uh, down to the main channel at Osable Chasm in upstate New York. Picture on the right, I'm surveying some of the erosional landscapes in the area known as Little Scotland on the island of Barbados. Okay, people, as far as rocks go, weathering is pretty rough stuff. Uh, Weathering involves the physical or mechanical breakdown or disintegration of rocks and minerals into smaller and smaller fragments. It could also involve the chemical decomposition of rocks and minerals. This will happen when rocks are exposed at the Earth's surface and subjected to the action of agents such as running water, groundwater, wind, ice, biological activity, etc. If you had a chance to review uh, my previous topic on the wild world of volcanoes, the next statement would make sense to you. Minerals that crystallize first in Bowen's reaction series are also the first to weather. As far as the picture, you can see potassium feldspar and quartz being weathered from granite. Erosion involves the physical removal of the weathered material by agents such as streams, glaciers, wind, mass wasting or landsliding, groundwater, etc. As far as the picture, you can see the Austin Chalk, which is a white limestone underlain by the Eagle Ford Shale. You can see the erosion of the limestone along the area that we call the Bosque Escarpment, which is a fault scarp in the city of Waco in Texas. So to stress the point or reiterate, physical weathering involves the mechanical breakdown of rocks and minerals into smaller and smaller fragments. Be aware that as particle size decreases, the surface area that becomes exposed to potential chemical weathering also increases. As far as the pictures on the left, you can see examples of physical weathering of granite. This area is called Enchanted Rock near the city of Fredericksburg in the state of Texas. The top picture at the top, I'm surveying some of the erosional landscapes in Nova Scotia in Canada. The physical weathering agent involve ice, like in frost wedging and frost heaving, that cause rocks to break into smaller fragments. Also running water through what we call hydraulic plucking, water moving fast and rushing into cracks, etc., causing rocks to break into smaller fragments. Running water also, as well as wind, can erode through the process of abrasion, which is friction, or if you will, the sandblasting effect. The action of organisms, biological activity, like plant roots, etc., can break rocks into pieces, contributing to physical weathering. Physical weathering can also involve the expansion through crystallization of saline solutions that will burst rocks apart. and also pressure release due to unloading, uh, generating fractures and creating channels for further weathering to occur. The picture on the left is an eroding stream at Oswald Chasm in upstate New York. Okay, so much for physical weathering. Now, chemical weathering involves the chemical decomposition and chemical alteration of rocks and minerals. One of the most effective agents of chemical weathering is carbonic acid, H2CO3. A diagram of what carbonic acid looks like is given on the left. You have one carbon atom surrounded by 3 atoms of oxygen and 2 atoms of hydrogen. Carbonic acid develops when water, H2O, combines with carbon dioxide, CO2, to create H2CO3, that being carbonic acid. The H2CO3 breaks apart into hydrogen cations and bicarbonate anions. Carbonic acid can react with calcium carbonate or calcite, which is the main component of limestone, to dissolve it, to break it apart into soluble calcium cations and bicarbonate anions. The bottom line is that carbonic acid can dissolve the calcite in limestone. Carbonic acid can also do a number on the feldspars. In the reaction shown here, you can see that potassium feldspar, the KAlSi3O8, reacts with carbonic acid and water to yield a brand new mineral, a clay mineral that we call kaolinite. That is the Al2Si2O5OH4. The bottom line is that feldspars weather into clay minerals. Climate is a critical factor in chemical weathering. Most chemical weathering occurs in tropical and subtropical climates. On the other hand, physical weathering is predominant in dry or arid climates. There are 4 main processes of chemical weathering. These include oxidation, hydration, hydrolysis, and carbonation. Oxidation involves the loss of electrons during a reaction by a molecule, atom, or ion. In this manner, oxide minerals are created. Hydration is the process of combining a substance chemically with water. In other words, introducing water into a mineral's chemical formula. Hydrolysis is the process of breaking mineral compounds using water. New minerals can be created during the process. And carbonation is, as we talked about before, the mixing of water and carbon dioxide to create carbonic acid. And as we saw before, carbonic acid can result in the dissolution of calcite and the chemical alteration of feldspars. Here I'm going to show you 2 examples of oxidation. The first one involves pyrite, fool's gold, iron sulfide or FeS2, weathering chemically into hematite, and iron oxide with formula Fe2O3. The second example involves olivine, one of the ferromagnesians, Fe2SiO4, also oxidizing into hematite. If you look at the reactions on top, you can see that pyrite reacts with water and oxygen to create iron sulfate and a very strong acid, sulfuric acid, the H2SO4. If heated enough, the iron sulfate will yield the iron oxide hematite plus sulfur dioxide and sulfur trioxide. In the second reaction, olivine, which is Fe2SiO4, reacts with carbonic acid to break apart into iron cations, bicarbonate anions, and silicic acid. The iron and the bicarbonate can combine with oxygen and water to create hematite, the iron oxide, plus carbonic acid. Here you can see examples of hydration and hydrolysis. In hydration, remember you're adding water into the chemical formula of a mineral. In the top reaction, you see calcium sulfate, which is anhydrite, breaking into uh, calcium cations and sulfate anions, and these combine with water to create gypsum, which is the calcium sulfate times 2H2O. The hydrolysis example is one that I have already given you, feldspar changing into clay. We discussed the reaction of potassium feldspar with carbonic acid and water to create the clay mineral that we call kaolinite, etc. And finally, we have the process that we call carbonation that we have talked about before, which is the combination of water and carbon dioxide to create carbonic acid. Uh, this process is critical, as we saw before, for example, in the dissolution of calcite, uh, and this process in itself is critical in the creation of cavern systems and cave systems. Okay, so we have now completed part 2. See you in part 3.